Hello. Welcome to SI for differential equations. This is week 6, I believe. And today we're going to talk about circuits and second order differential equations again. So maybe let's just hop right into it. Let's start out with a word problem here. Okay. And it reads as follows. Okay. Um, That's supposed to say capacitance. And one final assumption. Okay, so this is a pretty lengthy word problem, so let's just dissect it real quick. So it says at time t equals 0, current of 2 amps. That's important. Flows in an RLC circuit with resistance equal to 40 ohms. It's got inductance equal to 0.2 Henry. I like that unit. That's a good unit. And capacitance is equal to 1 over 10 to the 5th farad. And it says find the current flowing in the circuit at any time greater than 0 if the initial charge on the capacitance, the coulomb, and then it says assume that this right here, this EFT, is known as impressed voltage. We're going to assume it's equal to 0 for all t greater than 0. And now the thing about this RLC circuit is it runs on alternating current. So maybe I can just draw a quick schematic to give you a visual. So for circuits, we'll say our power supply is like right here. And then you have a resistor. And then you have a capacitor. And then you have, this is more squiggly and jagged. Then you have an inductor. I'm not too sure what the inductor looks like, but let's just assume that's what it is. So, the current is alternating. So it goes like that, and then it goes like that, but it happens so quick. It's almost instantaneous. And so that's just a little overview of alternating circuits. And now we want to set up an equation. So our general form for these sort of equations looks something like this. Okay. So that reads the inductance times the second derivative of the charge plus resistance times first derivative plus 1 over the capacitance times Q equals the impressed voltage, right? Okay. So, if that's the case, let's write out what all we know. Well, here, this time t equals 0 has a current 2 amps. That's actually an initial condition. There's one thing you might need to know is you have charge, right? And, well, what's current? It's simply just the flow of charge. And if you take a time derivative of that, it is exactly current. Or most of the time denoted as I for current. Okay? So, what I was going to say is a current of 2 amps. So, another way we could write that is Q prime of 0 is 2. Okay? And then let's keep reading. Flows, resistance. R is 40 ohms. L is 0.2. C is 1 over 10 to the 5th. Okay? Maybe let's just set up our equation. Oh, and also down here. E of t is equal to 0. So we know that this equation is going to be homogeneous, right? So let's set it up. 1 over 10 Q double prime plus the resistance, 40. 40 Q prime plus 1. Now, be careful. The general form is 1 over the capacitance, and our capacitance, oh no, what have I done? Oh no. Here, perfect. Sorry, I got sidetracked. Our capacitance is 1 over 10 to the 5th times Q. And that's all equal to 0, right? So maybe rewrite it once more. It's 10 to the 5th. Okay? And that's really something like that. Yeah, it's 100,000. And I want to multiply by 10 just to get rid of that fraction there. So it'll look something like this. Wait a minute. I've made a mistake. I knew I did. That 0.2 is not 1/10. It's 1/5. Okay. So, actually multiply by 5. Okay. So if that's the case, then 5 times 40 is simply 200. And this is 500,000 cubed. And now it looks pretty familiar, or hopefully it does. It's just a homogeneous second order differential. And you just let Q equal e to the Rx, derive it twice, and then we substitute in, right? Which implies that e to the Rx times R squared plus 200R plus 500,000 equals 0. And now, solve for R, it's a negative B, plus or minus t squared. What's this? All over that. Okay. Now I can tell you this radicand, whatever, under the radical here. That simplifies to a negative 1,960,000. Okay. And you can actually take the square root of that. Well, it's imaginary, of course. It's a negative number. But if you disregard the negative, you can take the square root of that big number there, and it leaves you 14,000 or 1,400. Yeah. So, if that's the case. R equals a negative 100 plus or minus. We have this 1,400 over 2i. Or in other words, 700i. Okay? Now, we can write our general solution. I should say the complementary solution, now that you all know what that is. But in this case, it's really the general solution because our impressed voltage is not changing with time. It's staying zero. So, if this is alpha, that's beta. Our solution would look something like this. T cosine of 700t C2 e t sine of 700t, right? Let me go back. So I forgot one initial condition, which is right here. The initial charge is 1. The initial charge is 1, so that's the case. We know Q naught is 1, right? So what I'm going to do is I'm going to go ahead and solve for one of these constants before I take the derivative of my charge here. So I just plug in 0, and it's going to leave me, I have 1 on this side, and a C1 here, and that's it. Because you plug in 0 for t over here, and it all goes to 0 because the sign of 0 is 0. So we know C1 is 1. Maybe we can look at this equation now. And now, what we have to do to find the charge, I'm sorry, not the charge. What we have to do to find the current is take that derivative, like I was saying. Current is simply the flow of charge. So, by taking its derivative, we have exactly that. And now here. Oops. Up a little. So I believe this first one is going to be right here at negative 700. Yeah. Maybe I'll just take the derivative first times derivative of the second. And then plus the second times the derivative of the first and then we have our next derivative right here, and I'm going to just leave my C2 outside. And then, just like how we did it before, first times derivative of the second plus the second times the derivative of the first. Right? Okay. So let's rewrite it. That first set of brackets is going to look something like this. Oops. E to the negative 100t cosine 700t. Okay. And then this bottom, C2, 700 e to the negative 100t cosine 700t minus 100 e to the negative 100t sine 700t. Okay. And now let's maybe go back and look at our initial condition. Was it right here? Yes. So Q prime of 0 is 2. So it's going to say 2 equals, and plugging in 0, I can tell you that this goes to 0. And this also goes to 0, right? Now if we look at these other ones, I think that's really just going to be negative 100 plus 7, I forgot my C2. 700 minus 100. Oh, I'm sorry. Second term went away. So yeah, it is just 700. C2. Right. So I hope I'm writing somewhat legible for you all to see. And now, all we have to do is solve for C2. Okay? So if that's the case, we add 100, it's 102 equals 700 C2, and C2 is 102 over 700. And I believe the problem asked for the current, right? Find the current flowing at any time greater than 0. Well, that's really just this formula right here. Well, I should say right here above it. But all you have to do is plug in that C2 and there's your formula. There's your current. Came out quite nice. I'm going to start another page here. Okay. All right, that was good. Maybe do one more here. Only this time, let's look at So once again, we're going to find the current. Actually, find the steady state current. And the current. For any t greater than 0. Okay. And we're given initial conditions, something like this. And then it also gives us our units here. Okay. So we have our RLC and some initial conditions. And before we get started, I just want to say, the steady state current it's defined as the derivative of the particular solution for the charge. So I repeat it. The steady state current is the derivative of the particular solution of the charge. Right? Okay. So let's set up our formula here. Okay. So if that's the case, we have 1 over 10 q double prime plus 3 q prime plus 1 over 100 cube. And now this one, the impressed voltage is not 0 for all t greater than 0. We're going to set it equal to 5 cosine 10t minus 5 sine of 10t. Okay. So we can attack it at 2 different angles. We can go for that complementary solution, which is solving for the homogeneous system, or we can just go straight for a particular and, equate coefficients and find it like that. So let's just start off with the complementary. So we'll look at this formula equation. And I'm going to multiply by 10, get rid of that fraction. I don't like that fraction. 1,000. And it's still 0. So I'm going to make a note. Solving for Q sub C. Okay? That's what we're doing right now. And from here, just like before, Q equal e to the Rx, and then take its derivative twice. Thus, this implies something like this. Equals 0. Okay? Then, solve for the roots. Solve for the roots. It's a negative plus or minus the square root. 3 squared. Minus 4ac all over 2. Okay. So, just real quick. 30 squared minus 4,000. This is going to be an interesting number. Okay. because this right here is a negative 3100. So we know we have imaginary roots again, since our radicand is negative. The question is how do we simplify it? Well, let's see. R is going to be a negative 15 plus or minus. If you remember way back, you can sort of factor out that middle part, right? Or that number, I should say. And from there, we can take a square root, and it looks something like that. Okay? Oh. Wait a minute. That's not... Yeah, okay. That's what I thought. So if that's the case, this is what we have multiplying I. And of course we have to divide the 10 by 2, so what we're left with is really just a 5 square root 31i. Okay. So we have our R, and now we can write out the complementary solution, and it will read something like this. Remember, alpha, this is beta. So 15t cosine of 5 squared 31t plus 2 e to the negative 15t sine 5 squared 31t. Okay. That's looking good. For now, I'm going to leave that as that, because I want to get on with the particular solution, because we haven't done one of those yet, and I want you all to see it. So, where was my equation? Here it is. So, it's of the form cosine and sine, so what we do is we also make an assumption about our Q of P. So now I'm going to say solving for Q of P. And if that's the case, I want to say let Q of P have the form A cosine, I believe it was a 10. Yes, 10. 10t plus B sine 10t. Right? And then, just like with the e to the x, the complementary solution, I should say, we take its derivative twice. And that will yield 10a sine 10t plus 10b cosine 10t. The second one is going to be negative 100a cosine 10t minus 100b sine of 10t. Right? Well, so you see, we had this function for our E of t, and to solve for the particular, you just let our solution be of the same form, and we take its derivative twice. And now, all we have to do is we have to plug these derivatives, these equations, into our original equation for the circuit to solve. Right? I'm just checking my work real quick. I don't make any mistakes. Okay. That looks good. No. It's going to be, let's see here. 1/10 Q double prime plus 3Q prime plus 100Q. So 1/10 of this negative 100a cosine 10t minus 100b sine of 10t. It's going to get very cramped. I can already tell you. Let's see. Plus 3. Negative 10a sine 10t plus 10b cosine 10t. Right? And lastly, we have 100 times that original q. So plus 100 times a cosine 10t plus b sine of 10t. Okay, and all that, it should be equal to this right here, what I already highlighted. Okay, but let's just put that in the back of our minds for now, because we really are only focusing on this left side for a while. So we have negative 10a cosine 10t minus 10b sine of 10t. And there I just multiplied that 1/10 out into that little expression there. And then I'm going to say, I might group that actually, plus that's going to be a negative 30a sine of 10t minus 30b cosine of 10t. Okay. And lastly, this out real quick. 100a cosine of 10t plus 100b sine of 10t. And it's all equal to just the same. Okay? Now, let's keep going. Okay? We want to get our sines and cosines grouped. Okay? So, first, I'm going to use a different color. Use green. See a cosine here. See a cosine here. See a cosine here. Okay. I'm going to use a different color. I see a sine here, I see a sine here, and a sine here. Okay. And now, I'm going to write all of those coefficients multiplying that cosine and sine. So first, I'm going to do the cosine. So I have a negative 10a. I have a negative 30b. And I have 100a. All that multiplying that cosine of 10t. And then we'll do the sines here. It's denoted with blue, my bad. Do the sines. You have a negative 10b. You have a minus 30a. We have a 100b. Okay? And that, of course, is the sine of 10t. Multiplying that. Now we are ready to equate coefficients. I can see the light at the end of the tunnel. I can see this problem coming to a close. So, this coefficient out front of this cosine is a 5, and the one out front of the sine is a negative 5, okay? So, we know this must equal 5, and then this must equal a negative 5, right? So now, also, I can do a little bit of simplification within these expressions here with my a's and b's, and I'll do that when I rewrite. So let's see, 90a minus 30b equals 5. And then again we have 90b minus 30a equals a negative 5. Okay. And from here, it's just, you have two equations, two unknowns. The system can be solved. Hallelujah. Let me do it. 90a equals 5 plus 30b. And a equals 5 over 90 plus a third. Sure. Okay? And so if that's the case, you just substitute that in for a. Whoops. Substitute that in for a. 90 plus 1/3. I don't like that. 1/3 equals negative 5, right? So again, I'll rewrite it. It looks like 5 over.
Mark, can you hear me?
Yes, I can hear you.
Can you please check the chat window?
There's a B missing. Oh no. Oh no. Which B am I missing? B over 3. B over 3. Is it in this step right here? Or is it before? Oh. Thank you. Yes. Right here. Ah. Okay. Yes. Okay. I'm sorry, I got carried away. I got a little too carried away there. I think, yeah, everything else has been good. Okay. So where were we? 30 over that. Well, thrown off a little. So let's do this. Negative 5. So this is really 10 there. And 30 goes into that. 30 goes into that 3 times. So you're just left with 5/3. Or maybe rewrite this again. Something like this. Okay. And now you have 100b. Ah, yes, this is looking good. Yes, this is exactly where I wanted it. Negative 5 plus a 5/3. And from here you have a negative 10/3. And divide by 100. You get negative 1/30. Now, since we have our b value, go back to a. Right here. So this implies that a is equal to 5 over 90 plus, what is it, negative 1 over 30? Yes. Negative 1 over 30b divided by 3. I'm not the best with fractions, so maybe I use my calculator to help me out. Also this b goes away. Oh, it's my mistake. Forgot the b, and then I decided to add one in. I don't know. And And so this is negative 1 over 90. So 4 over 90, and that could be simplified even further to 2 over 45, yes. So that is exactly A. And now we have a particular solution. And it looks like this. 2 over 45, okay. Cosine of, I believe, 10t minus 1 over 30 sine of 10t. And now, the problem wanted the steady state current. And as I already had defined, the steady state current is the derivative of our particular solution, which is something like this. Okay? And you can simplify this fraction if you want, but there you have it. We have found the steady state current for any time greater than 0. And with that, I'd like to thank you all for joining me today. It was a good session. And I hope this was somewhat helpful for you all. Excuse me. And I'll see you all next week. Thank you so much.